This section has to do with GPS segments. First of all, the diagram shows 3 segments of GPS. Global Positioning System is based on the interoperation of 3 distinct segments: the control segment, the space segment, and the user segment. Those 3 different segments communicate together to each other through radio signals. This diagram shows the concept of the space, user, and control segments in action, with satellites having an upload and download ability to share data. The user, in this case, is an aircraft, and monitor stations are part of the control segment along with the master control station. GPS satellites follow one of 6 orbital planes. And so there are 6 orbital planes in the GPS constellation. All the satellites in the GPS constellation face continuous change. They're always moving. There are 6 orbital planes, and each orbit is completed in 12 hours. 3 satellites are needed for a signal, and 4 satellites are visible at any point at any time from any point on the Earth's surface. The minimum number of satellites in a constellation is 24, and in reality, it's typically greater than 24, depending on operability of satellites at any given time. The control segment includes a set of ground monitoring stations that track the location and status of each satellite. The position of satellites must be known and is predictable. You can these satellites synchronize atomic clocks to within a few nanoseconds of each other. The Navstar GPS system includes the Master Control Center in Colorado Springs, plus 5 different control stations. The Department of Defense historically introduced random errors for security reasons, resulting in an intentional degradation of signals. And only the Defense Department had the ability to decode those errors and use more precise GPS positioning. In 2000, the U.S. government discontinued selective availability, and this increased the accuracy of GPS. One of the realities is that initially the United States was the only country that had a GPS constellation in orbit, but now there's more than one. So Russia has one, the European Space Agency has one, and several other countries do as well. And so as their data became more and more accurate, the reality was that increasingly precise data from GPS systems would be possible. And so the opening up of satellite signals in 2000 made a big difference in the availability of highly accurate GPS data. So these plots show positions collected over a 24-hour period, and they show the accuracy of GPS positioning with and without selective adaptability, pre-2000 and after 2000. So user segments include handheld devices, navigation units such as in vehicles, and mobile devices. GPS satellites run with atomic clocks, and satellites broadcast pseudo-random codes, and time differences between signal origin and receiver is used to calculate the positions. Distances are calculated as a function of the difference in the time of broadcast and reception of a GPS signal. A 2-dimensional location fix requires 3 satellites. Adding a fourth satellite allows a 3-dimensional location to show both horizontal and elevation positions. Here are the following: 1 satellite anywhere on the surface of the sphere, and 2 anywhere the spheres intersect, 3 where all 3 intersect, and then you can pinpoint a location. Satellite positions include 2 revolutions in 1 day. Prediction of satellite location can be important for field collection planning. Space trilateration includes 3-dimensional trilateration. It uses the geometry of triangles to determine positions. Known locations of 2 or more satellites are required, and measured distances between GPS receiver and each satellite. Absolute position is called a fix. More satellites allows for more accuracy. This shows the concept of trilateration. With 1 satellite, the surface of a sphere shows you that you really cannot pinpoint a location. With 2 satellites, you can begin to narrow it down quite considerably. But with 3 satellites, you can come up with 2 possible points. With 4 satellites, very certainly then 1 point. And here we see the concept. In 2 dimensions, you could determine your position using 2 ranges that would intersect at 2 points. Remember that in the previous diagram, where we had 4 satellites in operation, then you could look at 3-dimensional space. If clock error is introduced, your position will change because the 2 ranges will intersect at a different point. If there were no clock error, ranges from additional satellites would intersect at a single point, which is your position. From the intersection of 3 ranges with clock error, your position can be determined algebraically by solving for the unknowns in the equation. And this concludes this part of the lecture discussion.